opportunity to boost systems engineering teaching thanks to the virtual twin. To introduce you quickly the two companies, Dassault Systems is a French company specialized in digital solutions which offers people and companies virtual environments for the work. Quanser, on the other hand, is a Canadian company specialized in the elaboration of educative systems for the academic world, but also for the research world. What we're going to show you today is the coupling between one of the Quanser products, an aerospace device with 2 degrees of freedom, and its virtual twin, developed under the 3D experience platform of Dassault System. So during this webinar, we're going to go through 4 different parts. In the first one, we're going to explain to you what we did with this virtual twin and this aerospace device, and also why did this collaboration between Dassault System and Quanser took place. In the second part, we will present to you the real aerospace device developed by Quanser, the device as created in the first place by the Canadian company. Then in the third part, we will show you some demonstration about what it is possible to do with the virtual twin and with the real aerospace device. And finally, we will have some time for a session of questions and answer. I invite you to ask any question you may have in the chat during this webinar, and we will try to answer them at the end. So what exactly is this collaboration? The two companies wanted to collaborate in order to enrich the pedagogical experience initially developed by Quanser, the educative aerospace device, also called Quanser Aero. The aim was to use the Dassault System 3D experience platform to create a virtual twin of the real device, a kind of virtual helicopter whose behavior will be identical or almost identical to the real aerospace device. So what we did is that we created a 3D model of the aerospace device, but it's not simply a 3D model. We implemented multiphysics behavior to the 3D structure, which allow it to move and behave exactly like the real aerospace device. We are able to control the virtual twin almost exactly like the real device. For example, we can give a target angle for the pitch and the yaw axis of the virtual helicopter, and we will see how the virtual twin will dynamically try to reach the position. At any time, we can connect the real device to the 3D experience platform and see that the behavior of the real device is really similar than the one predicted by the virtual twin. So what exactly was the purpose of the collaboration? Well, the main goal was to extend the utilization of the real device. Imagine a classroom where every student can work independently on his virtual twin during several hours, and then in the end, he can confront the results of his simulation with the real aerospace device just by plugging it to his laptop. Well, that's an amazing perspective. The virtual twin also allows a kind of augmented vision of the reality. As it is a digital helicopter, we can add a lot of information like arrows to show the error of position of the helicopter, or even pieces of the helicopter which can change of colors depending on the temperature, the rotation speed, or any other information we can have. The virtual twin also allows to predict the impact of conception default, such as displacement of the angle of the rotor. Well, of course, all those concepts are the one that we're going to show you today, thanks to a few demonstrations. But first, let's start by a presentation of the real aerospace device. So this is the contour I was talking about, which looks like a helicopter with 2 degrees of freedom. It can move along this axis, the pitch axis, and this axis, the yaw axis. About its composition, it has 2 rotors, one main rotor here, which allows to control the pitch, and one tail rotor here, which allows to control the yaw. It has blades here, which are 3D printed and shipped by Quanser, but it's possible to print them yourself if you want. About the rotors, we have one DC motor here and one DC motor there. We have sensors on the Quanser arrow. one encoder here and one encoder there, which allow to know the position of the DC motor shaft and therefore of the blade propellers. We have one encoder here and one encoder there, which allow to know the pitch angle and the yaw angle. And we also have sensors which allow to know the speed of the blades and the intensity of the current within the motor. About what we can do, it's apply a voltage on the two motors, and you can apply a voltage from minus 18 volts to plus 18 volts. About the data acquisition system, it's integrally built in within the helicopter. We have here USB interface. So the only thing you have to do is plug a USB cable from the Quantum Aero to your laptop, install some drivers, and the Quantum Aero is ready to be used. So now that I have presented the real helicopter, the real aerospace device, which is next to me on the table, well, this is its virtual twin, which is also on the table near to a laptop and a chair. And here, this virtual twin of the real helicopter is a 3D structure which looks like the real helicopter, but more than being a 3D structure, it has all the multiphysics behaviors associated to the helicopter. So it's possible to control the virtual twin exactly like the real helicopter. So how is this done? It's done here thanks to the functional logical architecture. Well, I'm not going to go into details, but here you have the order block. Here you have the controlled command block. And here you have the mechanical block. But I'm not going to go into details. I think we're going to see that afterwards. So as we are in a digital world, in addition to the 3D structure, we can add different elements, such as display, which allows to see the speed of the motors for the two motors, the pitch angle here, the yaw angle here, but also the pitch set value and the yaw set value. We also have buttons here, which allow to interact during the simulation. So, for example, we can block the axis, block the pitch or block the yaw. We can push the pitch or push the yaw exactly like during the reality, where you want to push the helicopter. We can show the aerodynamic forces. I'm going to go first simulation to show you that. So here we can see the set values. So 0 degrees for the pitch and 80 degrees for the yaw. And you could see the helicopter move because the helicopter is trying to reach the set values that we decided. With the green arrow over there, which represent the distance between where the helicopter is now and where the helicopter should be. So this is something that is allowed thanks to the virtual twin, because obviously it's not possible to see it with the real device. So we can see the helicopter move, and I'm going to show you what it's possible to do. Like for example, by displaying the aerodynamical forces. So as you could see, the blue arrows represent the aerodynamical forces of the helicopter. I'm going to play it again so that you can see the forces over there. So during the simulation, I can also push the yaw. So here I am pushing the yaw, and we can see the blue arrow, which is showing that the helicopter is trying to resist to me pushing the yaw. So in this example, I think I push it with a force of 2 Newton. I'm doing the same thing here with the pitch. So the helicopter is trying to stabilize. It has some difficulties, but it depends on how the control is done. Here it's with a simple PID, which can be changed by myself or by the students, so it depends how the PID is chosen. To show you another simulation, I'm going to block the yaw right now, and we can see the green arrow here, which is the difference between where the helicopter is and where the helicopter should be. And as I block the axis, you can see that the helicopter cannot reach the position. So as I can block the yaw or block the pitch, we can control the helicopter only on 1 degree of freedom. So I'm going to show you an example here when we're going to ask him not to, when we're going to block the yaw. And so I put the 0 set value for the yaw. And for the pitch, I'm going to ask him to go to 0 degrees, then 20 degrees, then 0 degrees, then minus 20 degrees. Um, Tuck, tuck, tuck. Gonna go there. And as I said, we're gonna block the yaw. So I'm just gonna find the tree there. Simulate. We just have to wait 2 or 3 seconds. Mm, we just have to be patient. Okay, there we go. Okay. Tuck, tuck. So I'm gonna block the yaw. And what I also want to show you while the helicopter is starting is that we can, during the simulation at any time, we can plot some values, some curves. So here, what I can do with I can plot the pitch angle set value, and I can also plot the pitch angle value, and I can see them on the same graph to see how they behave over time. So here in red you have the set value, and in blue you have the actual pitch angle. So you can follow the evolution over time of the angle, which is very important if you want to do control. Well, yeah, if you want to do control. So in here the control is done with a PID, and you can change the gains of the PID at any time to see how the parameters of the PID will affect the simulation. So for example, we're going to change the values of the PID of the pitch. So there. So here you have the gain K, Ki, and Kd, which are the three gains of a PID. And here I'm just going to choose a point P. So I'm gonna cancel the I and cancel the D. So here it's like we have only a P corrector with a value of 15, with a gain of 15. And you're gonna be able to see the difference, the impact of the control on the helicopter, on its behavior. Just have to wait a bit. Come on. All right, there we go. Okay, so here you can see it's the typical behavior of a P controller. So you can totally see the difference with the PID. And here the P controller is not well tuned, but just to show you that it is possible really quickly and easily to change the parameters of a controller. Alright. So this is the first example of what it is possible to do. And to give you another example, what we can do with the virtual twin is simulate the impact of a default conception, of a conception default. For example, if the main rotor here has an offset angle of 5 or 10 degrees, well, we can simulate that. So how to do that? I just have to change one value of one constant here. I'm going to write 20 degrees, which is the constant defining the offset angle of the pitch rotor. And so after I've done that, I just need to simulate again. There is no calculation to do, no equation to write, just one constant to change, and the model is going to calculate everything for me. So I'm just going to wait 2 seconds, okay. And here you can see the offset angle. Well, I'm going to choose a better view, like this. All right, perfect. And here you can see the 20 degrees offset angle of the rotor. All right. So if I run the simulation and I show you the aerodynamical forces, we're going to see that the helicopter is going to have some difficulties to follow the set values. And we're even going to see the aerodynamical forces, which are not going to be vertical, but which is going to be shifted with the offset of 20 degrees. And this is why the helicopter has some difficulties to read the position. We can see here that it has 25 degrees, and on the previous simulation it was easier for the helicopter to reach the 20-degree set value than the 0 than the -20. Okay, so this is how we can simulate a conceptual default. And what I want to show you right now is that we can validate all those simulations with the real helicopter. And how to do that? Well, we can just connect the real helicopter to our laptop, to the 3D experience platform, and we can realize the exact same simulation, but with the real helicopter. So what we want is the exact same instruction block, the same command block, but we don't want to send the command to the virtual twin, we want to send it to the real helicopter. So for that, we have to make 3 clicks. So here I have to select the real helicopter and not the virtual one. I have to check that I have the good execution setup parameters. And I'm just gonna re-put the first scenario with the yaw going from 0 to 80 degrees over there. Okay, and the only thing that I have to do is to simulate, to run the simulation here up, and thanks to the camera you can see the real helicopter. I press play, and here we have the real helicopter, which is gonna have almost the same behavior than the virtual one with the previous simulation. Well, the behavior is not identical, but it's not the goal here. The aim of the virtual twin is to predict the behavior of the real helicopter, but realistic behavior, which 10% of error. But the goal is to be as accurate as possible. And so in here, at any moment, I can validate what I did virtually. I can add disturbances to the helicopter. So maybe I pushed it a bit too much. Okay, so that's okay. It was because we are at the end of the simulation. I just need to simulate again. There we go. Okay. So I can give disturbances to the helicopter with my finger. And so we can obviously do all the things that we did virtually. We can do them in the reality. I can also block the axis with the Allen key, which is there to block the yaw, or I can block the pitch with the screw which are over there. And what I want to show you is that we can also give an offset angle to the rotors. So with the Allen key over there, we can loosen the screws and give an angle of 20 degrees to the rotor. And so I can resimulate with the offset angle. All right. Okay. So we have the exact same simulation, but with the rotor shifted of 20 degrees. So the helicopter doesn't have that much issues to reach the position, but is a bit less accurate to reach the 20 degrees, then the 0 degrees, then the -20 degrees position. So this was to show you the duality virtual helicopter, real helicopter, which allows to validate in the reality what I did virtually. And now what I want to show you with the time left is something different, which is possible to do with the virtual twin, and that we call the instrumentalized virtual twin. So what is the instrumentalized virtual twin? So it's a virtual twin which is gonna be displayed when we control the real helicopter. Previously, when I was controlling the real helicopter, you didn't see anything on the 3D structure, on the 3D platform. What I want to see right now is when I control the real helicopter, I want to see the virtual one, which follows and replicates the behavior of the real helicopter. And as it is virtual and numerical, I can add a lot of information on the virtual twin to have more information than what I see on the real helicopter. I can have arrows, I can have pieces which change of colors depending on the temperature, the speeds. So it's like if we have more sensors, more information, and that's why we call it an instrumentalized virtual twin. It allows to see more things that only with your eyes watching the real helicopter. So you will understand better with the simulation. So we keep the control on the real helicopter. We just add the virtual twin up, and I just need to remember of removing the 20 degrees of the rotor offset angle. And the only thing that I need is to simulate once again. Have to wait a few seconds. Okay. Alright. So we have the virtual helicopter and the real helicopter at the same time over there. And I only controlling the real helicopter. So if I play up, all right. So we have the real helicopter on the right, uh, which is being controlled by the 3D experience platform. But at the same time, I have the virtual helicopter, which is following the helicopter, and which allow to display more information, such as the display over there, which allow to know the exact angle of the pitch and the exact angle of the yaw, because it's difficult to see it with your eyes. And we have the green arrow over there, which is the difference between what a helicopter is and what a helicopter should be. We can also have the blades, which can change of colors depending on the speed. I can make them become green or purple or whatever I want when the speed reaches, for example, 2000 RPM, revolution per minute. So with the second part of the virtual twin, the instrumentalized virtual twin, we can we can have more sensors than what it's possible to have on the real helicopter. We can simulate and model new sensors of the same sensors, which give more information and illustrate the informations better. So now we're done with the demonstration part. I hope that you understood the amazing possibilities given by the virtual twin and by the real device. Now I just want to spend a few minutes on the lectures and the hands-on that we developed here in Dassault Systems. Those lectures are completely free and they are available on the website of Dassault Systèmes. So the first lecture is about systems engineering process. It's a really quick lecture where students can understand what is a systems engineering process and they can apply this process on the Quanser Aero and its virtual twin. So basically we go down the V cycle, but every time we give an example with the Quanser Aero and with the virtual twin. About the hands-on, we developed 4 hands-on. The first one is about DC motor. When students can understand how does a motor work, how can we model this motor, and how can we control its speed with a really easy example. The second hands-on is about the electrical consumption, where the students are going to measure the electrical consumption of the real device, but also of the virtual twin. They're going to compare the results, and they're also going to play with some parameters of the helicopter to try and see which parameters modify have an influence on the electrical consumption. The third lecture is about control and dynamic control, where students are going to understand how does a PI, or a PID controller affect the behavior of the helicopter. On this lecture, the exercise is a bit like the one I showed you before. We're going to block the yaw axis. We're going to give an instruction to the pitch axis. Here it has to go to plus 10 degrees, then minus 10 degrees, then plus 20 degrees. And we're going to see how does a PI or PID controller tries to reach this position, try to make the helicopter reach this position. Finally, the last lecture is about the design and the industrialization of the blades. As I told you in the very beginning of the webinar, Quanser ships the Quanser Aero with 3D printed blades, but it's also possible to print our own blades. And on this lecture, the student is going to start by prototyping a blade that is different from the first one, and is going to go from the prototyping to the industrialization with the design of a mold at the end. So that is the end of the webinar. I hope that you enjoyed it, and I feel free to ask any question you may have. We're going to try to answer them as. Okay, so the first question that we have is from Joris, who is asking where the lectures will be available. So after the webinar, in 24 hours, you will receive an email with a web link. You can click on the link, and it will go directly to the 3DS Academy website. And in the website, you can find all the lectures that I just presented. For the moment, we just have the catalog courseware of the lectures, but next week, all the materials will be there. So the lectures, the hands-on, everything you need to run the lectures on your laptop. Okay, so that's the only question that we have for now. I'm going to stay here in case you ask any other questions. You can write them at the bottom of the GoToWebinar interface. And well, if you don't have any other question, you can leave the webinar, but you can also stay to hear people questions. So it's up to you. I will stay here for 5-10 minutes in case you have any question. And that's it. Some people are saying great presentation. Thank you. Well, thank you for attending. And well, don't hesitate to ask questions if you have some. Okay. Yeah, Krishna, I will answer the question personally after. I will send you an email with all the people that participated to the webinar. I won't say that publicly here. I will send you an email with all the information. Someone is asking what is DOF of the system. So what we mean by DOF, it's degree of freedom. So the helicopter has 2 degrees of freedom. It has the pitch axis and the yaw axis. So that's why sometimes we say a 2 DOF helicopter, because it's a helicopter with only 2 degrees of freedom. Did I answer your question? I know it's a bit long to write the question on the chat. Which PID controller is used from the same person? So we use 2 PIDs, one PID for the pitch water and one PID for the yaw. And the 2 PIDs are well, basic PIDs with a P, an I, and a D for each one, and they are done thanks to Modelica. Modelica is the language that we use for the logical block of the simulation. So it's a bit complex to explain you that now, but if you have never heard of Modelica, it's a language which allow to model multiphysics behavior. So electrical, mechanical, hydraulic systems. You can do almost everything with Modelica, and also control. So for the simulation here, we use the PID block, which is given by Modelica, and then we just have to choose the gains of P, of I, and of D. So for the pitch and also for the yaw. Any other question? Well, if you don't have any other question and have other things maybe to do that are urgent, do not hesitate to leave the webinar so that I can see the attendees leaving. I'm staying here until you have some questions. So if you want to leave, or just have to press the cross, and I will see you leave the webinar. What types of sensor are you using? So the question is from Aditya Shundi. So it depends if we control the real or the virtual helicopter. If we control the real helicopters, the sensors have been built by Quanser. So I don't really know what kind of sensor they're using. I can't really answer the question for them, but I can give you the contact if you want to ask a specific question about the sensors. And gyro accelerometer, the kind of sensor, but I don't have more information actually. I think for the speed of for the rotation speed of the rotors, they use how to say that, a kind of gyro sensor, but I do not really have more information. For the virtual helicopter, we use sensors provided by Modelica, by the Modelica library. So all the simulation is built thanks to Modelica. So you have all the sensors represented in Modelica libraries, and you can use them for your simulation. Okay, I hope I answered your question. And if you want more information, I can send you the contact of Quanser. You're welcome. Okay, so if you do not have any other question, I'm going to end the session. I will say 2 more minutes in case someone is writing a question right now. And well, if you don't have any other question, I will leave the webinar in 2 minutes. So thanks everyone for attending, and have a good day in India. I think it's the middle of the afternoon over there, so have a good beginning of evening. I don't know. How do you say that? Okay, no more questions. So thank you everyone. Bye bye. Have a good day.